Hi everyone. So this video is meant to supplement lessons 2.4 and 2.5. You should have already kind of taken a look at these graphs here, these four graphs that are drawn in for you in an exploration activity. And then I do want you to notice that this section of notes actually covers 2.4, 2.5, and 2.6. The 2.6 portion we're going to cover in class when I see you again next. So I am going to be skipping around just a little bit here, and then the things that we jump over, you'll be picking up when I see you in class. Okay, so in the exploration activity, you should have become familiar with these four graphs. Okay, this is the direct variation function, and this is the direct square variation function. We have some other names for these, right? This is a line, this is a linear function. Okay, and I'll just put linear in here. And this shape here, let's see how I'm going to squeeze this in here. But the shape is called a parabola. The type of equation is called a quadratic. So if I use those words, you'll know what I'm referring to. Okay, and then you should have also noticed in the exploration that when you make that k value negative, it's actually the same effect on both graphs. What really happens is your graph flips upside down. Okay, so on the line, this end goes down here, this end goes up here. With the parabola, both ends flip down this way. Okay, so a k value is going to take your graph and tip it upside down if it's negative. So a couple of things about these functions we need to talk about today. First one is average rate of change, which you'll see down there at the end of the screen. Actually, I'm going to do this for now. I know it might make you mad, but I want to talk just about rate of change for a second. Average rate of change is the overall change in a function's dependent variable compared to the change in the independent variable on a specific interval of the function. That sounds like a lot of words. I'm going to boil it down here for you quick. By the way, if you need time to copy down that definition, feel free to pause the video. Change in the function's dependent variable. Typically for dependent variable, we use the letter y, right? Compared to the independent variable, which we usually use x for. So if I was to say this in a more simpler way, I would say change in y compared to change in x. If I made it even more simple, change in y could be referred to as rise, and change in x could be referred to as run. So what I'm really talking about here is rise over run. That should sound familiar to you. Okay, you've talked about this before. And in fact, that should sound an awful lot like slope, which is the word that's coming up next here. Okay, and that's true. Rate of change and slope are very closely related. Here's the thing with rate of change. We can calculate rate of change on any type of function. So we can do it on linear functions, we can do it on quadratics, we can do it on these guys that we're going to learn about, next time I see you. So you can do rate of change for anything. The difference is when you're on a straight line, the rate of change is constant, and that's why it gets a special name, okay? That when we're talking about a linear function, the rate of change is constant, okay? And the fact that it's constant means it gets a special name called slope. But slope really is a rate of change, okay? And in fact, so for both of these things, we're going to say that the formula for rate of change, otherwise known as slope, is y2 minus y1 over x2 minus x1. And I think you've seen that before. I hope that you've seen that before. Okay, so this is the formula we're using to calculate rate of change. Like I said, the difference is on a linear function, if I pick this point and this point and I calculate rate of change, I'm going to get exactly the same value as if I pick this point and this point way down here. It doesn't matter how far apart they are. It doesn't matter if they're right next to each other. I'm going to get the same rate of change no matter which 2 points I pick. But if I'm looking at a parabola, if I do rate of change between these 2 points, that's going to be significantly different than if I do rate of change between these 2 points. Okay, there's this section here and there's this section here. That's going to show two very different rates of change. So that's what this interval thing is talking about, in a specific interval. Because when we're talking about functions other than linear functions, it really matters which 2 points we're grabbing and using. Okay? So you can calculate rate of change from this point to this point is the idea. You do have a couple other words here. You have asymptote and limit. Don't bother right now pausing the video and getting those written down. Those are things that are going to come up when we talk lesson 2.6. Okay? So for right now, I kind of just want to go on to this first example about calculating rate of change. So we've got the function y equals negative 3x squared, and I want the rate of change between x equals 1 and x equals 2. This is that interval that that definition was talking about. Okay? Well, to find rate of change, as soon as I see rate of change, I'm thinking this. y2 minus y1 over x2 minus x1. Well, right now I only have x's to work with, right? I need some y values. So what I'm going to do is I'm going to take each one of these, and this is what I would do every time I have a rate of change problem, and I'm going to turn them into coordinates. I'm going to make this 1 comma something, and I'm going to make this 2 comma something. And to figure out the somethings, I'm plugging this 1 into this function. So negative 3 times 1 squared. I'm going to put that in my calculator, not because I need the calculator, but I just want you to see what calculation I'm doing here. I'm doing negative 3 times 1 squared. Okay, and I get negative 3. And then I'm going to do the same thing with the 2. So I'm going to change this guy to a 2. So negative 3 times 2 squared, and I get negative 12. So now using those 2 points, I'm going to calculate rate of change. So I would go negative 12 minus negative 3. Notice I use 2 minuses because there should be a minus from the formula and a minus from that number, over x2 minus x1. Well, negative 12 minus negative 3, that really becomes like a plus. So this is negative 12 plus 3, or negative 9 over 1. And so then I would say that my rate of change, is not negative 1, negative 9. Okay, that's the rate of change between x equals 1 and x equals 2. Essentially what I'm saying there is that between x equals 1 and x equals 2, for every 1 step you take along the x-axis, your y value is dropping by 9. But you're going to see that that's different when I go between 2 and 5. So let's do the same thing with our coordinates. Now I already have the x equals 2 coordinate, 2 comma negative 12. I'm going to do the 5, so I would go 5, and then let's see. 5 squared is 25, and then 25 times negative 3 is negative 75. And so for rate of change, I'm going to go negative 75 minus negative 12 over 5 minus 2. So this is really going to be a plus, right? 2 negatives make a positive. So negative 75 plus 12 would be negative 63 over 3. And negative 63 over 3 is negative 21. So that's my rate of change in that interval. And so what this is really saying is if I were to look at this thing on a graph and I were to look between 2 and 5 and kind of connect that segment in there, that segment would be much steeper. It drops much faster than this one does. Okay? So now let's look at what happens when we do that with a linear function. I'm going to do the exact same thing. Now this is a real simple one, right? Just 5x. So this would be 1 comma 5. This would be 2 comma 10. And when I calculate this, I'm going to go 10 minus 5 over 2 minus 1. That's 5 over 1, which is 5. Now let's go between x equals 2 and x equals 5. So again, I have the 2 coordinate already from the last problem. For 5, that's going to be 5 comma, nope, not 10, 25, sorry. And so then I would go 25 minus 10 over 5 minus 2. Well, that's 15 over 3, which, hey, look at that. It equals 5. The exact same thing, okay? And so the truth is, because this one is linear, because this is a linear function, I could pick any 2 x values I wanted and repeat this process, and this answer will always come out the same, okay? So that's why we call this number, that's why it gets its own fancy name, this gets to be the slope. By the way, did you notice that that's also the number that's sitting up here, okay? this here gives you the slope in a linear function. And you already kind of know that from working with mx plus b, but just so you have it in the context of variation, there it is. And so you might want to make a note that in a linear function, or I guess we should say in a direct variation function, I'm going to throw the word linear in here too. In a linear direct variation function, the k value tells you lots of things about the equation, but it also tells you your slope. Okay, that's an important observation there. Okay, that's really about it. So your responsibility is, and you should have done some of this already, but you should have, oh, I guess I don't have it here. You should have a table in your notes on the next page to fill out that you should be able to fill out based on the exploration activity you did. You should then have an assignment to do, and then tomorrow when you come in, we'll fill in those other graphs and definitions and the other half of your table. Okay? Have a great night.